All right, everybody. Chapter 11 here, lecture video 2. This one is going to be a particularly short one, only a couple of slides to talk about in this particular video. And that's actually going to already be the end of chapter 11 here. So it's a quick one. But here we go. Okay, right along. Now, Avogadro's Law is the title of this slide. Now, we previously mentioned in the last class, in the last video, that there are three main laws regarding gases. Okay, and it was Boyle's law, Charles' law, and Montan's law. Right, all three of those laws were able to be combined together to create that combined gas law that we spent a lot of class time talking about last time we met. Okay. Now we can add one more additional layer here to these three gas laws to give us a fourth one now, which is this Avogadro's law. And this Avogadro's law is relating moles to volume. Okay, moles to volume. Now, moles is something that we talked about towards the end of our sort of midterm section of this class, right? Moles was basically the main sort of gist of chapter 6 and 8, or the last two chapters we covered before the midterm. So what we've got here for Avogadro's law is this. The moles of a gas, right? So thinking about moles being the amount of particles of that substance, the amount or moles of gas are directly related to the volume of a gas. So now the graph ends up looking pretty much like this, where we've got volume on the y-axis here, moles on the x-axis here, and now we've got this nice sort of 45-degree angle for our like sort of darkish bluish purple line right there. Okay, so that shows the relationship here. It is a direct relationship. So basically saying this, as the number of moles of a substance increase or the volume increases, so does the amount of that gas, right? So if I have more moles, that the more amount, right, the larger amount of that gas I have, the more space, the more volume it's going to take up. So as the number or the amount of moles go up, the volume that those moles take up, the volume of that gas that takes up is going to increase as well. Okay, and that's Avogadro's law. We'll tie that Avogadro's law back to the other four gas laws in just a second. But I want to break in kind of talk a bit more about this kinetic molecular theory that we sort of started this chapter with, and add some more additional things here, because knowing all the ins and outs of this KMT or kinetic molecular theory is going to be very, very important. So molecules always in terms of gases move in random straight line motion. Okay, we can think about this might not be something you guys know all too well yourselves, but think about the little DVD. If you ever have a DVD player and the DVD is idling, right? Suddenly the idle screen will change, and now you've got that DVD symbol slowly moving in one direction and bouncing and hitting the walls and going back and forth slowly, right? That DVD symbol bouncing at each, the top, bottom, left, and right of your screen are bouncing and moving in random straight line motion. Okay, so you can think of that as you would the DVD logo in when it comes to idle moving of a DVD, right? So molecules move that exact same way, random straight line motion. So they don't like weave and dodge and move in any particular way like that. They always move in a random straight line motion. Okay, now the volume of a gas is negligible. Why is this the case, right? Why is the volume of gas negligible? Again, because the volume of the gas doesn't really matter. What matters more so is the volume of the container the gas is in. So the volume of the gas itself is always dependent on the volume of the container or the volume of the room that it's in. So the gas itself doesn't really have a volume. It's negligible. But the volume that the gas, or the volume that the container volume of the room is more so important than the volume of the gas. Okay. Not only that, but because the gas molecules are so far apart from each other as well, right? Think of the particle diagram I showed you guys at the very beginning a couple of days ago of gases, right? The dots and the particles of gases are so far away from each other that the volume of the gas itself is sort of negligible in that particular way too. Okay. Now, gas molecules themselves, individual gas particles and atoms molecules, have no attraction for each other, right? So you can't think of them like you would any kind of bonding situation, right? Where you've got ionic bonding, where you've got some attraction between positive and negative ions bonding together, if that's an attraction. Or you've got different atoms of a covalent molecule bonding because they're sharing electrons, right? Using that idea of electronegativity, right? Those are all different forms of attraction. In gas molecules, there is none of that. There is no attraction of each individual molecule of oxygen or molecule of CO2. Those CO2 or those O2 oxygen molecules don't have attraction for each other. Now, when these atoms, these molecules of gas are in their random straight line motion, like we've got right here, okay, there is sometimes going to be collisions, right? There's going to be some collisions, right? Think about bumper cars, for example. These collisions are what's going to be called elastic collisions, okay? Elastic collisions basically show that there's always a transfer of energy between these particles, right? So when there are collisions, they're completely elastic. And when there is an elastic collision, there's a transfer of energy between particles, right? So think about bumper cars, right? If you have two bumper cars coming head on like this, and they head on and hit, they don't just hit and stop. They go, hit, and they kind of bounce backwards like this, right? Because all the energy from the one on the right here transfers to the left, saying this one back. But the one on the left also comes in and hits it to transfer this one to the right. So they both kind of hit and bump backwards. Okay, that's elastic movement. So there's always a transfer of energy when any of those particles do in fact hit and create a collision with each other. Now, the next gas law here is going to kind of rope in the combined gas law with this Avogadro's law I showed you a minute ago, right? Because now we've got this idea of moles happening here. We've got this idea of moles now here, right? So now we have to add in, right? We've obviously previously talked about pressure, volume, and temperature, right? Now we have to add this fourth variable in here, which is moles. And we do that by talking specifically about the ideal gas law. Okay, an ideal gas law is any gas that obeys the kinetic molecular theory, right? So we utilize this ideal gas law. Gases behave like an ideal gas if they obey all of these different particular things of the kinetic molecular theory, right? As long as they are moving in random straight line motion, their volume is negligible, their gas molecules are not going to attract each other, and their collisions are elastic, and they transfer energy between the particles, that's going to be consistent of following all the different measures of kinetic molecular theory. And if a gas follows all of these different rules for kinetic molecular theory, they're going to behave and be labeled as an ideal gas. If that's the case, if we can label a gas like an ideal gas, that's going to be a situation where gases are going to be most ideal at high temperature and low pressure. So gases are most ideal when their temperature is really, really, really high and the pressure on them is very, very, very low. Okay, you flip that, having low temperature and high pressure, those are perfect examples of gases not being labeled as ideal gases. Okay, now the actual ideal gas law formula is as follows. Right, it's a lot of different variables here, but a couple of similarities and two main differences here. P, V, and T, right? Capital P, capital V, and capital T are still the same ones we know and love, okay? Pressure and volume and temperature. Now we have the added layer of this lowercase n and this uppercase r that are the newer ones here. So let's go one by one here and show you exactly what each one is. Again, not surprising at all, is P for pressure, okay? Watch how I specifically have very, very specific units for each of these different variables here. In this case here with pressure, notice how when we use the combined gas law, we really used an array of different pressures, right? We used atmospheres, ATM, we used kPa or kilopascal, we used mmHg or millimeters of mercury. But in this particular case here, with this equation, PV equals nRT, we need to use atmospheres. We can only ever use atmospheres, ATMs, okay? So pressure has to be labeled in ATM. Next up is volume. Same deal, right? Capital V, of course, is volume, but volume was either milliliters, ml, or just liters, L. In this particular case here, with the ideal gas law, volume needs to be in liters only, right? Not milliliters, has to be in liters. The next one up here is that lowercase n. Guys, this is going to be that idea of moles here, moles of gas, MOL, right? Our unit, of course, for moles is MOL, moles. So the number of moles given to us is a pretty basic number. Oftentimes it's going to be 1 or 2 or 3, or it's going to basically be whole numbers here, right? So the number of moles of a gas is going to be a whole number, and we're just going to label it with MOL like we're used to doing, right? Moles is labeled as MOL. Now, next up is this capital R. This is what's known as the gas law constant, okay? Unfortunately, like you see here, Okay, you've got to memorize this thing. Now, what the heck is this capital R? The constant is 0.0821. And now we've got this very, very funky looking unit here. Okay, this unit here in its entirety is liters times atmosphere divided by moles times Kelvin. Okay, guys, we have to think of this unit just like we would think of these units here. Okay, so this is just a unit. This is not some kind of equation baked into this number here. It's just a unit, just like you would see that you've got 2 feet. Well, feet is the unit. Well, same thing here. Liters times atmosphere divided by moles times Kelvin is the unit. All right. This will make a bit more sense as we progress through and actually do an example problem in this when I see you guys in class next. But let's just hold on to this for right now. But again, start to memorize this. Okay. This capital R value, 0.0821, needs to be memorized. It's nowhere in your reference tables. I'm not going to really ever give it to you. Okay. So you have to memorize this. And then, of course, lastly is temperature. Capital T, right? Again, recognizing, guys, that K or Kelvin here is only form of only unit of temperature we need to use. Okay, that's not super unfamiliar to us, right? Because the same thing kind of held true and rang true with our combined gas law, right? P1V1 over T1 formula. All of our measurements of temperature, of course, in that one also needed to be in Kelvin. So nothing particularly new here. But again, notice how, however, last thing I'll say, and that'll be it for the video here. Notice how all 4 of these values here, all of these units, ATMs or atmospheres, liters, moles, and Kelvin. All 4 of these, atmospheres, liters, moles, and Kelvin, are just so happen to be present in this unit for our value of R, our gas law constant. Okay, we've got liters here and liters here. We've got atmospheres here and atmospheres here. We've got moles right here and moles right here. And we've got Kelvin right here and Kelvin right here. So guys, that is the exact reason why all 4 of these variables, pressure, volume, moles, and temperature, need to be in these units exactly, atmospheres, liters, moles, and Kelvin. If they're not, they kind of clash. They clash with the unit for the gas constant here, R. And then, so let's say if I've got milliliters instead here, well, milliliters is not the same as liters, so it clashes with this unit here, right? So we would have to change this from milliliters to liters, okay? So again, it's important to recognize that pressure, volume, moles, and temperature need to be in atmospheres, liters, moles, and Kelvin because of this R constant here and its unit, all right? Guys, that's the end of the video. I'll see you in class.